So my agenda today is more of an introduction talk. So I'm going to talk about Flink architecture, sizing and monitoring, and I'm going to share some customer stories along the lines. Apologies for the English. So in Flink, we have kind of two major components. The first one is the job manager. It's basically in Kubernetes going to be a pod, and we're going to have at least one or more task managers in the usual cluster deployment, right? We can have a standalone kind of single node deployment, but this is not what we're here to discuss. And the job manager is, has two jobs, really. The first thing is to schedule jobs. An application that's submitted to Flink is really something that we call a job, right? So any kind of SQL query or a submission of a main method in a jar file or whatever that creates a job graph for Flink, that would be submitted through the job manager. And then each of the task managers have something we call task slots. So each of those slots basically can be occupied by whatever parallelism the task has, the job has. So if we have a job with parallelism of 2, we'll have 2 task slots occupied. And that's how Flink kind of achieves horizontal scaling, through increasing parallelism and increasing number of slots available theoretically. I'm going to go back to this in a bit. All right, so there are 2 ways, really, to submit jobs in Flink, 2 kind of paradigms, if you will. The first is the application cluster, where the job manager is in charge of starting the application. So the job manager submits kind of starts the main method of our program, creates a job graph, and this binds the job manager to a specific job. The second one is something we call the session cluster, where we have a job manager and a separate client is in charge of submitting the job, either through the UI or the REST API or whatever you will have. And in this case, the session cluster can, of course, run a single job, where resource distribution is a bit easier, right? So we can have job manager run a single job, but have many task managers. And this is how we can maybe manage resources in a slightly easier method. And it can run multiple jobs, especially if we have short, batchy, or maybe low scale jobs, or we're serving multiple tenants. Either way, in this case, we can have a session cluster. When we have fault tolerance in Flink, right? So when we need to restart a job or anything of these lines, there are multiple components when running on Kubernetes. So the first thing is that the job manager is going to maintain the cluster state in some kind of config map. That's the first thing. So in Kubernetes, the job manager creates a config map, and it basically uses it as kind of a key value store. So it will save all the list of running jobs, and it will do leader election through the Kubernetes API, etc. And that's how the job manager kind of can do all these consensus decisions. There's only a single real job manager that's in charge of the cluster, and most deployments you'll see will have a single real job manager. But if we're very sensitive to downtime, and we don't want to have this single point of failure, we can have this, let me go back. We can have this kind of mechanism where we have standby job managers who will basically be elected maybe faster if the main job manager goes down. So if we have a node replacement on Kubernetes or whatever, we don't have to wait for the pod to be rescheduled. It will be slightly faster if a standby job manager is elected. If we want to be able to promote a standby job manager, we need to obviously think of a couple more things. So the first of the job manager is in charge of coordinating checkpointing and scheduling, and being and it needs to persist, like the blobs that were used to start the job, like Python scripts or jars or whatever. So it also needs to persist some data in a persisted store. So in Kubernetes or in the cloud, that could be S3 or anything along these lines. So you'd have a result store and a job graph and a blob store all saved on S3. And that's when there's a re-election, the next job manager can pick up the data from there. Next, each one of our running applications or jobs also keeps some state in Kubernetes. One of them is what is the current checkpoint. So there's an increment in the checkpoint number, and there's a pointer basically in the config map that says what's the ID of the next checkpoint. The next thing is where are all the current completed checkpoints located, and a little bit more metadata. when Flink runs the checkpoint, that's when the state of our running tasks and each of our operators really gets flushed down into object storage or whatever, and those are saved also in a distributed manner, usually in S3. So that's either the checkpoint metadata or the state snapshots. All right, so having kind of thrown all this information at you, let's just discuss about what are your options or what are your considerations when you're trying to plan your Flink deployment from an operations perspective. So the first thing is, are we going to run application or session clusters? And if we're going to choose session clusters, even if they're only meant for a single job, for proper resource kind of allocation and separating concerns, how are we going to do that? Next thing is to basically size our task managers. How much CPU are they going to have? How much RAM? How do we manage the Flink memory model? What kind of disks are we attaching? Do we want attached NVMe disks for fast state access in case we really have a huge RocksDB? Or can we just use a simple, or we don't need a disk at all, we can just use the ephemeral storage on the Kubernetes host. And another thing to consider is that our jobs are going to have basically one of two kind of working patterns. The first one is when there's a sudden spike of traffic, that can either be simply because we just restarted the job and we need to do some catch up, right? So if we took the job down for maintenance, then we can expect that there's going to be some slight burst when the job is suddenly restarted. So at that point, we're going to have some catch-up time where the resources consumption is going to be higher than the average that we usually experience. So whenever you kind of look at your Flink job and you're saying, oh, well, it's only taking 1 or 2 CPUs in average consumption, you kind of need to think about that catch-up time. So that's another thing to always remember. And this next thing, when you're thinking about your task manager, is basically the memory model. So the Flink memory model, we usually define it at the process level, and then the rest of the components, we give a fraction of that process memory to. So Flink uses both on-heap and off-heap memory. On-heap is mostly used for the internal usage of the framework, and then basically the user, what we call the user space, the user code. So the thread stack, new objects, everything there usually happens on the heap. And then there's off-heap memory that Flink manages. The majority of it, or the main usage of it, is going to be for 2 things. The first is RocksDB. If we're using the embedded RocksDB backend, Flink can manage RocksDB for you and basically manage the memory consumption of RocksDB. In this case, you're going to have basically 40% of your cluster off-heap memory allocated to RocksDB by default. If you're not using an embedded RocksDB backend and you're using a hash map state backend, or if you're lucky and you're using some service that has something like the Gemini state backend or whatever, you can take the managed memory. Well, Gemini, you need it anyway, but if you're using just a hash map state backend, you can take the managed memory fraction down to 0 because it will not be used. You don't have state on basically off heap. Next, there's basically some direct memory allocations that Flink uses. The more important one is the network buffers that's allocated off heap. Flink uses network buffers for transferring information between the task managers. So for example, in Daniel's example from before, he had a key buy operator, and that key buy by product ID, I guess, needs to shuffle data around to guarantee that all data from a specific product arrives at the same task slot, and that subtask really handles all the data for the window of that slot. So those network buffers are going to be used. And we want to make sure that there are always available memory segments or network memory segments. There are 32 kilobyte chunks that are used as memory segments. And we want to make sure that those are available. The next is intermediate data in task off heap, if it was enabled, and some framework off heap for a bunch of Flink objects. Then some usual cause of mischief is the JVM metaspace. That's by default 256 megabytes. That's basically class initiation, method initiation, fields, whatever, all the JVM nice stuff. It's by default 256 megabytes. If you have a lot of classes, a lot of methods, a lot of fields, and you like kind of monolithic jars that have data for 700 jobs like we do, that thing might need to be increased. The next thing you need to think about is kind of what to monitor for our Flink jobs. So these are my top 4, if I had to put any. The first thing is job uptime. So for long-running streaming jobs, job uptime or restart time is really the more interesting fact. And we want to make sure that even though we might have fault tolerance and our applications can restart quickly, we want to make sure that they're actually always running correctly. So we want to measure that we don't really have downtime in a long-running stream processing application. The second part is if you have a job, a batch job, where you just submit, let's say, a Flink SQL query, and you want to dump some data from Kafka topic in a batch process down to S3, you definitely want to make sure that it doesn't take too long. So a batch process should be basically able to scale, right, to finish in basically whatever SLA we give it. And we usually want to set alerts if it's taking too long. The next part is checkpointing. So in a streaming job, whenever we have stateful operations, let's say we are counting words, or we are tracking the latest price of a stock, or whatever, we're going to periodically snapshot our state down to distributed storage in case the job goes down and we need to restore it. So there are a couple of main points here. I'm not going to touch on the full checkpointing mechanism in Flink. That deserves 30 minutes of its own. But there are 4 main things to monitor. The first thing is the duration. How long does it take me to end-to-end initiate a checkpoint, dump all the state to S3, etc. And then, what is the size of my snapshot? The time it takes me is one of the components that impact how long it's going to take is what is the size of my state. So if we have really huge state in one of our operators, or the operator is skewed or whatever, it's obviously going to take longer to dump the snapshot. The second thing, or the third thing really, is the alignment time. So if we're using unaligned checkpoints, that means that all the parallelized Flink tasks in our job need to actually reach a checkpoint barrier before we can start dumping the state. That's how Flink aligns kind of all the different parts to checkpoint at the same time. And if you have a long alignment time, let's say one of your tasks is skewed, you're going to have a start delay where a checkpoint is not really starting. And then you're likely going to see other slots just waiting on the delayed slot finishing its checkpointing time. Once slot 1 and 2 arrive the barrier, there's no more processing they can do until the third task slot finishes. As a bypass of that, you always want to measure throughput and end-to-end latency. So you want to make sure that your number of records and your processing times are correct. And as usual for any kind of computing system, we want to make sure that our system metrics are aligned. So CPU, all the JVM memory, whether it's on heap, off heap, or whatever, threads, I/O. We just want to make sure that we have resources if we need them, and we're not starving our system. And anyway, I'm going to share one of our customer stories. So Luca's a blockchain analytics company. They track a lot of blockchain data, and they use Flink basically to calculate a lot of stream processed aggregations. So a lot of state, a lot of windows, a lot of other things. They have many jobs, many stateful operators. And in some jobs, they were not meeting SLA. They had issues with checkpoint alignment, causing some of their subtasks to have a 10-second delay sometimes. They had some issues submitting the jobs correctly to Kubernetes. They were basically encountering multiple processes of the same, multiple submissions of the same jobs running because of some operator bug. And they had requirements for 0 downtime upgrades. So they cannot have any downtime when they're upgrading their cluster. And that's a tough one to achieve. And if 0 downtime upgrades was tough, they also needed automatic failover to a backup region, which is where I wanted to quit, but I couldn't. So I'm going to share kind of how we helped them achieve those. So the first thing was at their processing rate and at their jobs, it made sense to convert most of their kind of main pipeline processes from exactly once to at least once. So they're reading and writing back to Kafka in most of their intermediate jobs, and that meant that there was another dedupe layer that we could use in the customer-facing jobs at the end of the pipeline. So the decision to go to at least once means that we don't have to go through the Kafka transaction process, which means that we initiate a transaction by the internal producer of the Kafka sink, and then every message we basically process at the sink, eventually there's a checkpoint, and as part of the checkpoint process, the Flink producer will commit the transaction to Kafka, and then that basically has the weight of a two-step checkpointing, right? That's how Flink can achieve it exactly once, but the overhead was just huge. We had issues with Kafka transactions just exploding, or other kind of different problems that were not worth it at most of their jobs. And the second thing we did was we moved in some of those jobs to unaligned checkpoints. So we stopped aligning the checkpoint times, and that's a configuration that if your parallel or distributed data store, the source data store is distributed, you can do that, and you can enjoy from not having the inter-task dependency on checkpointing. And the next thing is we looked at all their state access and kind of RocksDB mechanisms. And basically one of the problems with exactly once in RocksDB is that you have a lot of compactions as part of the checkpoint process. And once you can space those out a bit, they become more efficient and works a bit better. Also, we started compressing the snapshots, which meant the upload time to S3 in jobs with huge state were a bit better. And we did some code improvements to make the classes a bit easier to serialize and deserialize. And we basically, given all those, managed to go down to sub-second checkpointing, basically. Another improvement we thought of, but ended up not doing because of the next feature we had to implement, was checkpointing to something that is not S3, but a faster storage, so an EBS volume or anything of these lines. The next thing we had to tackle was they needed a zero downtime upgrades, and they needed failover region. Sorry, it still makes me laugh thinking about it. So we had to basically create our own orchestrator, really, that is some extension of the control plane that basically handles job submissions, handles the version upgrade in a kind of awkward way, backs up the state to a failover region in case we need to redeploy the job, and knows how to trigger the region failover if needed. So this is how their version deployment pattern looks like when they need to redeploy. So the control plane triggers the Kubernetes and creates a Kubernetes manifest to create a new cluster. A job manager and a task managers are created. And the current cluster is still running at this point. The control plane triggers a save point on the current cluster, whatever we call the main cluster at this point. And it submits the new job into the new cluster to start from that save point. So we basically copied the state. We triggered our own save point of the state, and we submitted the job from that save point. After that, there's a grace period where we give the new cluster some time to succeed checkpointing and make sure that it's alive and well. Obviously, the downside of this grace period is that we now have duplicate records. As we mentioned earlier, we took the dedupe out of the Flink job responsibility, put it in another place where we use some kind of fast key value store. And after we're sure that the new cluster is alive and well, we tear down the old cluster and after canceling the job. So that means that we have a new cluster started from the manual save point that we triggered, and we can stop duplicating our efforts. And in a regional failover, it's basically the same mechanism. The control plane takes periodic save points that it copies to an S3 bucket in the failover region. So if we're on US East 1, on AWS, for example, we trigger the save point, and we make it save that save point in a US East 2 bucket, for example. That was cheaper than copying every checkpoint file using S3 replication, which was the previous solution. And also, it was easier to initiate a new save point, a job from that saved save point, and it helped us basically work it out a little bit better. To understand the interval at which we had to take those save points, we had to measure kind of the burst capacity. So our task manager sizing, going back to the first slides, we had to think basically how much catch-up are we going to have to do, and what does it mean to our SLA. Basically, there was if we have a failover region, we need to recover within 15 minutes or whatever. So that's how we measured the burst capacity, and we understood that we need to take that incremental save point every 10 or 15 minutes, something along these lines. So once the failover is triggered, that's a system-wide thing. Obviously, all the systems over there have basically some kind of disaster recovery implementation in a backup region. So the control plane, which is in itself distributed and fail-safe, et cetera, creates the deployment on the fallback region once it's triggered. And that's not as straightforward as we thought it would be, because it turns out that we might have taken a save point on region 1, but the Kafka offsets were different. So maybe the mirror maker replication from Kafka in region A to Kafka in region B did not catch up yet. And we had to do some extra processing before submitting the new job to handle the alignment between the replicated Kafka topic and what we had in the checkpoint. So we had to basically go back save points until we found the latest one that we could use. And we did that with the state API. You can just open the checkpoint, read the metadata, and understand kind of where were the checkpoints in all of those partitions. All right, so yeah, that was it. Happy to take any questions. And I will never have to use this clicker again.